Unit 6, Gases, Lecture 2, Dalton's Law. And with Dalton's Law, we're going to look particularly at gases collected over water. Gases are very frequently collected by bubbling them through water and catching them in a bottle. Many, many years ago, they did this first with mercury, but then they found water was better, probably a lot less, not only a lot less dangerous, but probably a lot easier to handle. But in any case, if the gas being collected is carbon dioxide, yeah, then what's the composition of the gas in the bottle? So you collected carbon dioxide, but what was in the bottle to start out with? Well, we started out with the water, and the water was pushed down by the carbon dioxide, wasn't it? So the composition of the gas in the bottle now is carbon dioxide saturated with water vapor. So the total pressure in there is the pressure of the gas plus the pressure of the water vapor. 340 milliliters of a gas is collected over water at 20 degrees Celsius, and the barometer reads 758 torr. Let's find the volume of the dry gas at the same conditions. How are we going to do this? We've got to know the vapor pressure of water. Well, there's a table of vapor pressures. So you've got to check a table of vapor pressures to find the vapor pressure of water at 20 degrees Celsius. And the vapor pressure of water at 20 degrees Celsius is 17.5 torr. So we take our 340 milliliters of our gas. Now that gas is feeling a pressure of 758 torr minus the vapor pressure of water. So we have something less than 758 torr, and we want to find the volume of the dry gas at 758 torr by itself. So we're going from something less than 758 torr up to 758 torr. We're going to increase the pressure, which of course is going to reduce the volume. And when we work it through, we find that the volume of the dry gas at those same conditions is 332 milliliters. That's right, 332 milliliters. We didn't have to do any temperature changes because the temperature didn't change. The only thing that changed here was the pressure. This time we're taking the same quantity of gas, but we're setting up the situation to be a little different. We have 340 milliliters of gas collected over water at 20 degrees Celsius and a barometric pressure of 758 torr. But this time we want to find the volume of the dry gas at STP. So we start out looking up the VP of water, and the vapor pressure of water at 20 degrees Celsius is 17.5 torr. That's right, because we collected it over water. So we take our 340 milliliters of gas. Now, we have to allow, of course, for the 17.5 torr. The barometric pressure is 758 torr. So we take our 340 milliliters of gas times 758 minus 17.5 torr over 760. Because we're taking this gas from a pressure that is less than 1 atmosphere up to standard pressure, which is 1 atmosphere. So we're going to be increasing the pressure, and when we do, it's going to decrease the volume. Then we multiply this by 273 kelvins over 293 kelvins. Again, because we've collected this gas at 293 kelvins, and we want to find the volume at standard temperature, 273. And when I work this through, I come up with 309 milliliters as the volume of the dry gas, the gas after I've removed the water and have set it to be a volume at standard conditions. Graham's law. Graham's law deals with rapid and random motion of gases, which allows them to escape through even tiny, tiny openings. This rapid and random motion of a gas molecule results in effusion. That is the term we use for the escape of gas molecules through tiny openings. Now, the rate of this motion is related to the kinetic energy of the molecules. The higher the kinetic energy, the faster the motion. The lower the kinetic energy, the slower the motion. Or we could show it this way. E sub k is equal to 1/2 the mass times the average velocity squared. Now, E sub k is the same thing as ke. Sometimes you see it as ke, sometimes you see it as E sub k. So I'm using it here so you'll get used to seeing it both ways. But an important question arises. What is the impact of temperature on kinetic energy? Well, folks, as we increase the temperature, the velocity of these molecules increases, right? So we see the impact of temperature right here on the average velocity. Therefore, the kinetic energy of a gas is directly related to its temperature. Remember that. The kinetic energy of a gas is directly related to its temperature. Graham's law often is stated like this. The rate of diffusion of different gases at the same conditions. The rates of diffusion are inversely proportional to the square roots of the molecular masses. Now, I'm not going to derive it for you, but it can be derived from the expression we just saw. The rate of A, the rate of effusion of A, times the square root of the gram molecular weight of A is equal to the rate of diffusion of B times the square root of the gram molecular weight of B. But what do we mean by rates? Now, this we need to clear up, absolutely. Rates are distance per unit time as a rule. But you can think of rates as milliliters per second. You can think of it as feet per minute. Or get this, a perfectly legitimate way of talking about rate is 1 over time, the reciprocal of time. 1 unit of a gas moving in a particular time. You can't ever say that the rate of diffusion of a gas is 15 seconds, for example. No, that's time. That's not rate. Rate has to be something per unit time. Don't forget that. If oxygen effuses from a container at 3.64 milliliters per second, what is the molecular weight or gram molecular weight of a gas effusing from the same container at 4.48 milliliters per second? Well, we're going to use this expression. And let's see, let's let A be oxygen. So it is going to effuse at 3.64 milliliters per second times the square root of 32 grams per mole. Yeah, the molecular weight of oxygen. It's got to be O2, remember? And that is equal to the rate of effusion of B, which happens to be 4.48 milliliters per second, times the square root of the molecular weight of B. Well, when you work this through, you find that the square root of the molecular weight of B is equal to 4.50. Now, how do you solve it? You solve it by, I know you know this, but I just have got to remind you that you solve this by squaring both sides, so that the square root of the molecular mass of B times the square root of the molecular mass of B is going to be equal to the molecular mass of B. And that is equal to 4.50 squared, which is 21 grams per mole. And that's the way you work it. Be careful how you handle radicals. Stoichiometry. You've seen this heading come up several times before, haven't you? Well, in this case, this is simply a combination of, much that we've already studied, plus, of course, our gas laws. Calculate the weight of zinc needed to react with hydrochloric acid in order to produce enough hydrogen to fill 3 250 milliliter bottles at 28 degrees Celsius and 738 torr. Well, what do we need to do? First, we need to write an equation. And here it is. And when the equation is balanced, we have a 2 in front of our hydrochloric acid. Yeah. Now, let's find the moles of gas, and then we will find the moles and mass of the zinc, which is what we're after. So let's start first with the moles of the gas. Well, we can use PV equals nRT, and we're going after the moles. The pressure is 738 torr over 760 torr per atmosphere times the volume. Well, we've got 3 bottles at 250 liters at 0.250 liters per bottle, 250 milliliters per bottle. And that's going to give us moles times 0.0821 liter atmospheres per mole Kelvin times 301 kelvins. Now, stop for a minute and solve this. And when you do, watch your units also. See how bottles cancel bottles and liters cancel liters and on and on. Then when you solve it, you find that the moles is 0.0295 moles of hydrogen. Okay, we've got the hydrogen now, the number of moles. So we take our 0.0295 moles hydrogen times a 1-to-1 mole ratio, because the ratio of hydrogen to zinc is 1-to-1, times 65.4 grams per mole for zinc, and that tells us that we're going to need 1.9 grams zinc in order to react with this hydrochloric acid to produce that amount of hydrogen. Now, folks, an equation is based on standard conditions, is the way you should look at this. So if you're working with a gas at conditions other than standard conditions, and you need to have that gas engaged with something else in an equation, remember to get that gas to STP first. Then you can work your equation and not have to worry about the changes in temperature and pressure that the gas may have experienced if you've already converted it. Calculate the volume of nitric oxide produced when 2.5 grams copper reacts with excess nitric acid and the gas is collected at 30.24 inches of mercury and 31 degrees Celsius. And here's the equation. The reason we went ahead and gave you this equation that was already balanced is this is an oxidation-reduction reaction, and we have not yet balanced equations by oxidation-reduction techniques, so we'll give you this one. Now let's see. We're going to start with 2.5 grams of copper, find out how much gas is produced, and then find out what volume that gas would be at these other conditions. I'm going to do the problem in 2 parts. I'm going to start with 2.5 grams of copper and convert it to moles. And 1 mole of copper is 63.5 grams. Now I'm at moles of copper. I'm going to go to moles of nitric oxide, and the mole-to-mole ratio is 2:3. Now I am going to assume at first that this is at standard conditions. So I'm going to multiply this then by 22.4 liters per mole. And when I do this, I come out with 0.5875 liters. Did you get that? Now that is the volume at STP, standard conditions. Now I have to convert from STP to these other conditions. And I'm going to do it this way. 0.5875 liters times. And if you don't mind, I'm going to take pressure first. We want the pressure at 30.24 inches of mercury. But the pressure right now is standard pressure. And standard pressure is 29.92 inches of mercury. That's something you're supposed to know. We're going to take it from 29.92 inches to 30.24 inches. That's an increase in pressure, which will do what to the volume? That's right, it will reduce the volume. So we multiply it by 29.92 over 30.24. And if you want to, put inches here and inches here, but you know they will cancel. Now, the next conversion we have to make has to do with temperature. We have this currently at 273, but we want to take it to 31 degrees Celsius. And 31 degrees Celsius is 304 kelvins. So we're going to take it from 273 to 304. And when we do, that increase in temperature will make the gas want to expand. So let's deal with that. Expanding the gas would make, increasing the temperature would make the gas want to expand. So I multiply it by 304 over 273. Now we have two factors working against each other here. The pressure says the gas volume will be smaller. The temperature says the gas volume will be larger. Work them out this way, and this comes out to be 0.65 liters. Now, quite frankly, I would be delighted to see you do all of this in one step, because you see we went through, worked it out, came out with this answer, and then introduced this answer again here. It would be so nice if we could start at this point right here and bring in all of the things we did before and work it out in one fell swoop, which is certainly reasonable and a good way to handle it. Just be careful with your units. Kinetic molecular theory. The kinetic molecular theory of gases, well, it's really a kinetic molecular model. It's a way of talking about gases that allows us to try to understand and predict what is going to happen. But in any way, this model summarizes a lot of those characteristics we've already been talking about. Gas molecules are in constant motion until they strike each other or the walls of their container. A gas is composed of predominantly empty space. Molecules are so very tiny when compared to the space they occupy. Forces of attraction exist between gas molecules, but they exist significantly at the instant of collision. That's when they're close enough to have these forces of attraction become predominant. The total energy of a gas is constant. That's part of our model. The kinetic energy of a gas is directly related to the absolute temperature, the Kelvin temperature. I think we need to look more closely at this last statement. The kinetic energy, which is E sub k, for a mole of gas particles can be expressed as this. The kinetic energy is equal to 1/2 the molar mass times the mean square speed. Now, when we talk about mean square speed, what we're talking about is the average speed squared. What you do is you take a series of velocities, you square each one, add them up, and divide by the number of velocities used. And that gives you essentially your mean square speed. Well, we know this. Further, we also know that we're representing molar mass with m, and the bar means average. So u squared, bar u squared, is the mean square speed of the particles we're talking about. But we also know that for an ideal gas, PV equals 1/3 n times the molecular mass times the mean square speed. Now, I'm not going to get into where this comes from. You're just going to have to live with that one. You'll get into it when you get into PChem. But what I would like for you to do is substitute one of these equations into the other. Pause this video for a moment and make that substitution. Upon substitution, this is what we get. The kinetic energy is equal to 3/2 RT. 3/2 RT. Folks, nothing is said about the molecular mass of the gas. Nothing is said about the identity of the gas. The only thing the kinetic energy depends on is the temperature, the Kelvin temperature. It doesn't matter if a gas is pure or if it's a mixture. It doesn't matter what the gas is. So the kinetic energy of a gas depends on and only on the temperature. Does the identity of the gas matter? No, it doesn't. Does it matter whether the gas is a single substance or a mixture? No, it doesn't. Well, what matters? The temperature, the absolute temperature. Here's a handy table. You're going to run into R, a constant, and we've already talked about it some, but you're going to run into it in a lot of different circumstances. And I just thought you might be interested in seeing some of these commonly used values for R. Well, let's look at root mean square speed now. Root mean square speed, or root mean speed, is the speed of a molecule having the average molecular kinetic energy. It's the average. If you consider PV equals 1/3 n times the molecular mass times the mean square speed, and PV equals nRT, then you can take one to be equivalent to the other, simplify, and when you do, you will get the mean square speed being equal to 3RT over the molecular mass. So, to find the root mean square speed, just take the square root of both sides. And the root mean square speed is equal to the square root of 3RT over the molecular mass. What does the root mean square speed depend on? It depends on two things. It depends on the temperature, the absolute temperature, and the molecular mass. So as the molecular mass increases, the root mean square speed goes down. As the temperature increases, the root mean square speed goes up. Now get it straight. Let's look at a Maxwell-Boltzman distribution curve. This is a very, very interesting entity that is going to mean a lot to you as you go further in chemistry. I want you to notice that the temperature is increasing. And as the temperature increases, the molecular speed, and I have it here in meters per second, but the molecular speed is increasing. I want you to notice that you've got two different curves. This is the curve at the lower temperature. Notice the molecular speeds are much closer together, and there's a much greater number of molecules at each of those speeds. At the higher temperature, the molecular speeds are spread out more, and the curve is elongated and flattened. Now pay attention to this. This along here, let's assume that this is your leaving velocity, that when the molecules reach this velocity, that they will be able to leave and go off as a gas, if you will. That's going to mean a lot to us when we start talking about evaporation and those kinds of characteristics a little later in the course. Deviations from ideality. Real gases may be quite different from ideal gases. You see, gas molecules really may have a very significant volume. Well, not that significant, but they may have a significant volume when compared to the volume they occupy, if you will. And gas molecules could have significant attraction for one another. Under what circumstances does this occur? Well, the attraction for one another really increases when molecules are forced close together, low temperature, high pressure. So we find that as temperature and pressure of a gas change, then the relationship among the gas molecules change, and we really are not ideal anymore. What we need, folks, is the van der Waals equation. The van der Waals equation is this: pressure plus A times n squared over v squared times volume minus n times b is equal to nRT. Well, it looks kind of like the ideal gas law equation, doesn't it? Except for those added things, that factor that's added to pressure and that factor that's subtracted from volume. Well, you need to know what A and B stand for. Now, N is moles and V is volume, and N is moles and in the second half. But A adjusts for attractive forces. A adjusts for attractive forces. And B adjusts for size of the molecules. That's right. These two, through intensive experimentation, have been found to be the values that we need to correct the errors in ideal gas laws to make them correct and more realistic for the conditions we may run into. And you will see tables that give you these constants, A and B, for a variety of gases. Let's try a problem. Let's calculate the pressure exerted by 3 moles of chlorine gas held in a 10-liter container at minus 40 degrees Celsius and 1200 torr. But let's do it using both methods. Let's start with the ideal gases, and then from there we will go to the van der Waals. So let's use the ideal gas law first. PV equals nRT. The pressure is going to be that which we're looking for. We're going to find the ideal pressure first. The ideal pressure times 10 liters is going to be equal to 3 moles times R, 0.0821 liter atmospheres per mole Kelvin, times 233 kelvins. When you run this through and calculate it, punch it through your calculator, I came out that under the ideal gas law, the pressure came out to be 5.74 atmospheres. Okay, now let's look at the van der Waals equation. Pressure plus A times n squared over v squared, quantity, times volume minus NB, quantity, is equal to nRT. I'm going to have to reduce the size of the print somewhat in order to get these things on the screen. So look in your textbook for the constants. Remember, this is 3 moles of chlorine gas in a 10-liter container. All right, here we go. The pressure plus the constant of 6.493 liters squared atmospheres per mole squared times 3 squared moles squared over 10 squared liters squared. Now, don't forget when you're putting your units in here to square those units also. That quantity times 10 liters minus 3 moles times 0.05622 liters per mole. That's the quantity or the constant B that we have. And that is going to be equal to 3 moles times 0.0821 liter atmospheres per mole Kelvin times 233 kelvins. Now, I'm going to pause for a minute and let you run this through, but actually you would be better off pausing this video for a moment, running the calculations, and then double checking my answer. But when I run the calculations, I come through to see that the pressure is equal to 5.25 atmospheres. Now what we need to do is compare the results. When we compare the results of this, we found that using the ideal gas law, the pressure was 5.74 atmospheres. But when we used the van der Waals equation, the pressure was 5.25 atmospheres. That is a significant difference. And that difference is laid to the attraction among molecules as well as the actual volume of the molecules themselves. And because it's chlorine, a big molecule, they have a lot of attraction for each other. It's in a cold temperature, minus 40 degrees Celsius. The pressure is high, 1200 torr. That is going to be circumstances under which the van der Waals equation gives us the realistic answer, while the ideal gas law just doesn't fit the bill. Well, we've, after a brief introduction, talked about properties of gases. We went through a number of the gas laws, most of which you've seen before. We dealt with a little bit of stoichiometry, which just adds into all of that we have covered in the past. And then we spent some time on the kinetic molecular theory. A better way to teach and learn chemistry.